So hello together. Today I want to come back to our resistive power divider. We already discussed this in an exercise and we found if I have a 50 ohm system, this is our resistive power divider, and we are looking for the resistors here so that we have no reflections at the input and port 1, port 2, port 2 and port 3, and we found as a solution we must use a resistor which is a third of the characteristic impedance. So if I have a 50 ohm system, I must use a 60.6 ohm resistor, and then we found this to be our S matrix, and it's free of self-reflections and all parameters are 1/2. And of course we can also give now the parameter in the dB scale, which corresponds which corresponds to the diagram log mag in our network analyzer. And if I change to the dB scale, then we have here that S11 is given by minus 6.06 dB. This means, of course, a resistive power divider will always show a certain insertion loss. And now I want to discuss just some advantages. So a very interesting point is that the resistive power divider is extremely broadband. So this is a power divider which goes down to the DC, and of course depending on the resistors it has a small size. As a disadvantage we have that we have of course an insertion loss compared to a lossless power divider, and between the ports there is no isolation. And now I want to use the simulation tool to simulate the frequency behavior of our resistive power divider. And normally we should have to include the parasitics of R, but in the simulation I will just include here later a capacitor which will account for the capacitance of the solder point of this resistor. Of course this will be a parasitic element, and of course this will have an influence of the frequency response of our power divider. So now we go to the simulation program. The simulation of our resistive power divider, I use a simulation tool, and this simulation tool, as you know, you can download from my homepage, which is connected to my YouTube channel. So in the first step we take the resistor here, and we know that this resistor must have a value of 16.6 ohm. And of course we must use here these connections to be able to connect the other resistors. And again we take the resistors now here to build our resistive power divider. So this is our 3-port now, and as measurement equipment we take our network analyzer. And of course you see now this network analyzer has a coaxial input and a coaxial output. So it's connected here to the ground, so also we can now connect the input of our network analyzer to the port 1 of our resistive power divider, and we can connect the output of our network analyzer to the output of our power divider, to one of the outputs of the power divider. But you see here we would have an open port now, but to measure really the S parameter, for example, from 1 to 2 as 2, 1, we must terminate this port into a 50 ohm resistance, so that this is terminated with the characteristic impedance. So we take here a 50 ohm, and of course we must connect this 50 ohm resistance to the ground. And now we are also already able to do the analysis of our resistive power divider. And if I do the analysis, of course, as 1, 1 will have a 0 value which would account for minus infinite dB, but we are more interested in the transmission factor, so for example as 2, 1. And you see now this is the transmission factor as 2, 1. And we see now, for example, with the help of the marker function, we can read out that this has a value of minus 6 dB as we proposed in the preceding exercise. And since we did not include any parasitics to the resistors, or any parasitics of the resistors, we will have essentially no frequency dependence. And of course we could, for example, also change the frequency. I want to change the frequency to lower frequencies here. For example, I take 100 megahertz to 10 gigahertz only, and I want to use an exponential scale. And if we do the analysis now, we have in principle the same behavior, because we did not include any parasitics into our setup. And to demonstrate at least the influence of a parasitic, I want to include now a 1 picofarad capacitor, which would, for example, account for the capacitance of this solder point. So you must solder these resistors together, and of course then I assume this would result in a capacitance of 1 picofarad against ground. And if I do now the simulation or the analysis, then you will see that for high frequencies this capacitor will result, of course, in a short-circuited ground. This means now the insertion loss becomes bigger, and of course then we also will see some reflections now. You see this. Now you see the capacitor will result that, for example, the reflector as a reflection coefficient as 1, 1 will increase with increasing frequency. So again, the parasitics of our circuit will of course change the frequency behavior, and to really have a realistic simulation we should have to include some parasitics of the resistors and also some parasitics, for example, of connectors and so on. But this here is now a first simulation of a resistive power divider which would include at least one parasitic element. Parasitic element means it's an element that will occur even though I do not want to have it. So thank you for watching this video.